For the discussion, I'm going to follow the instructions of the organizers, and I'm going to summarize the talks quickly so that we can save most of our time for questions and discussion. So I'm going to quickly summarize the 4 talks in this session, and then we'll open to questions, and then hope we can have the speaker share slides if needed for the questions. The idea is to try to keep it moving. Okay, so with that explanation, let me just quickly go through the talks in this session. So in this session, we had Wang, we heard from him related to the talk now, and then Soubhik, Kumar, Mark Wise, and Sebastien Reneaux-Petel. So Wang gave a talk very closely related to Xing, so non-standard quantum clocks. He was similarly interested in this question of can we probe the relationship between the scale factor and time, focusing on these oscillatory signals, and similarly had some discussion of the different types of non-Gaussianity and how it depends on K. So I think there's a lot of overlap with Xing, and so perhaps some of the questions that will come up are related as well to Xing's talk. Okay, so we had Soubhik Kumar, who was talking about the cosmological collider. So this is similar, but now in the context of inflation. This, I believe, came up in one of the questions. The idea was, can you construct models that overcome the Boltzmann suppression in the context of inflation? So normally, when you have these massive fields, they produce these interesting signals, but they're Boltzmann suppressed. And so Soubhik wrote down this particular model, I think was one of the emphasis of the talk, where by using, so in one particular way of representing this interaction, it became this time-dependent source that, using the time dependence of the background could create the particles, and led to this large amount of, these much larger FNLs for this oscillatory massive signal. So we see these lines for various values of the coupling, and by dialing that, they could extend the reach and mass to up to 60 times Hubble, where 60 times Hubble is the scale of the time dependence of the background. He also talked about enhancing the signal using the curvaton, where the idea here is that the couplings of the curvaton are less restricted than the couplings to the inflaton itself, and so you can boost the background signal. Okay, so then we had Mark Wise, who was talking about 2 topics, the bispectrum of galaxies and going to conformal Fermi coordinates in quasi-single field. So the first part of the talk focused on the signal in galaxies from primordial non-Gaussianity. So this is related to the fact that galaxies are biased objects. So in a certain sense, even their power spectrum probes higher point correlation functions. So he showed how to do these calculations in various ways, keeping higher order contributions that come from biasing. And so this included both the power spectrum and bispectrum from these calculations. And then in the second part of the talk, he talked about transformations to conformal Fermi coordinates in quasi-single field, and how this is related to the problem of observability, as going to Fermi normal coordinates. It's known in single field that this cancels the effect in the squeeze limit, and they saw some partial cancellation, but that the signal survived when looking at bispectrum. Okay, and finally we had Sebastien, who was talking about a somewhat different topic, a manifestly covariant approach to multifield stochastic inflation. Here, the question was how to write the equations for stochastic inflation in a multi-field parameter space in a way that respects the geometry of the field space. And so they, did I miss a? Okay, I think I missed something. Okay, so they're pointing out a problem, which is that the sort of standard way of writing this down does not appear to respect the covariance properties. It doesn't transform covariantly under redefinitions of the metric on this space. So you'd expect to see, say, Christoffel symbols, for example, and not just Vierbeins. And so he walked through the ways in which this problem can be resolved. And I have questions about how exactly this happened, but I think ultimately it was tied in part to when you calculate these metrics using the full quantum mechanical description, and was able to resolve this problem and write down the full answer given here. And then in the second part of the talk, he explained how you can get this by starting from the full path integral and deriving the equations that way. Okay, so that were my lightning summaries. In principle, everyone was supposed to have watched those talks and have questions. So maybe we'll go through in order. Since we had many questions, but actually maybe we'll start. We'll go in order as I presented it, in case people still have some questions for you or Xingang from their talk, and then we'll continue. But I'll try to keep on time so that we have time for questions from everyone. So okay, let's start with questions for Yi or perhaps for Xingang. Any questions on sort of the primordial clocks, alternatives to inflation? Feel free to raise your hand or speak up however you like. You can add the question to the chat if you want me to ask it instead. But okay, so I have Soubhik. You can go ahead. Soubhik, I see your name. Raised hand.
Is he unmuted?
Oh, there you go. Let's unmute.
He is unmuted, but somehow we can't hear him.
Do you want to type it in and I can ask it? We can't hear you. Okay, anyone else have questions? We'll wait for him to type the question.
Maybe I can ask a question for Xingang and Yi.
Sure, go for it.
Since here you are also considering the time-dependent mass, right? The mass is there's this time dependence in this non-standard clock scenario.
Yeah.
And I'm wondering if you consider the scale dependence of the signal in the bispectrum as well.
Excuse me, scale dependence of the power spectrum, or
in the bispectrum, since previously the signal is the shape dependent one, right?
Right, exactly. So I think that depends on different kind of non-standard clock. So let me say within what we did. What we did is the masses of the Hubble parameter in alternative to inflation, and that if you only look at the squeezed limit, that can mimic inflation. If you only look at the shape dependence, it mimic inflation. But if you look at the scale dependence, that's different from inflation. Actually, it's pretty lucky that if you look at the dimensionless shape function, then for inflation, it is decreasing as if we have the long wavelength become longer and longer. The signal is decreasing. And for all the alternative to inflation, defined by absolute value of p is smaller than 1. So all alternative to inflation scenarios, the corresponding quantity is increasing when we are making the long wavelength longer and longer in the squeezed limit. So here, actually, for contraction scenario is more obvious, but otherwise it's out of the calculation of the correlation function. So that is the way that we can it can help to distinguish inflation and alternative.
Yeah, I guess the signal here might be, I mean, this is scale dependent signal might be helpful to distinguish the standard clock with the non-standard clock, since for the standard clock, there's no scale dependence. Right.
Oh, actually, let me just a quick comment. Sorry about that for interruption. I think you started the quantum case, right? So it's not scale dependence, still shape dependence, but you mean envelope.
First, I started quantum case, but quantum case for alternative to inflation. So there is a built-in scale dependence for alternative to inflation. the scale dependence of Hubble.
Yeah, but the scale dependence, the power, positive or minus you mentioned, is still as a function of a shape of two momentums, right? A ratio of two momentums, right? It's the envelope. It's the envelope of the oscillation.
Okay. Okay. Yeah. Thank you for your comment. Yes. Right. So. Right. Yeah. Actually, I'm right. Yeah. Sorry. Yes, I'm talking about the shape. Yes, the shape dependence.
Yeah. The envelope behavior of the oscillations. Yeah.
Right.
As a function of shape.
Yeah. So that depends on. So since I'm keeping one momentum, changing another. Yeah. So. It's more, well, there is a little bit of scale difference, but it's right, it's more shape dependence. Yes, thank you.
Yeah, actually, if you look at the scale dependence, I probably expect similar things will happen too, because those signals are not, it's hard for them to appear exactly scale invariant.
Yes, exactly. Since previously I studied the case with the running mass, right? And there will be also running in the scale dependent channel, and this running actually is different from the running in the shape dependent one. So I guess maybe something similar would happen here as well.
Okay, so we have the written question from Soubhik, which says, Yi, in your talk, you mentioned, you talked about generalized inflationary scenarios giving p less than 1. Are there alternative inflation scenarios that give rise to p much greater than 1? So I think this is, can you fake it the other way?
Right, so if p itself is much greater than 1, that will be, if p is much greater than 1 and expanding, that's just inflation by definition. And if p much greater than 1 contracting, that means modes are not going out of horizon, so that doesn't solve the horizon problem. And p much smaller than -1 and expanding, that's superinflation, where it's faster than exponential inflation. And p much smaller than -1 contracting doesn't solve horizon problem.
I'm going to guess he meant that in the signal part itself. Is that right? That just the expression for the signal. Okay, can you try again, Soubhik?
Yeah.
Is that right? Okay. Oh, we can hear you now. Go for it. Does that answer your question, or do you have, was that?
Yeah, I guess I was more going along the lines of like faking the signal, but I think, yeah, I mean, I don't want to take up too much time, so I can ask it later. Yeah, that's also fine. Yeah, thanks. Yep.
Okay, do we have more questions?
Is there any value of P for which you have enhanced symmetry? Like, you know, for inflation, you have all of these extra symmetries, boosts, and so on. Is there something similar for other values of P?
Definitely for p equal to 0, that's Minkowski space. But otherwise, that's a good question. Yeah. I haven't thought about that before.
Thanks.
Yeah,
it's an excellent question whether some symmetry argument can be used for some alternative background.
Yeah, so in terms of the calculation, if you talk about the Hankel functions, then indeed there are some special value of p that Hankel function reduced to sine cosine. Yeah, but I haven't thought about the symmetry argument.
Yeah, exactly. So if you want to look at the symmetries, at least when p equal to 1/2, things get very analytical. So maybe there are special things happen there. That's from our just experience. But exactly, that's a very good question. Yeah, p equal to 1/2, everything is analytical control. Not everything, a lot of them. Yeah.
Interesting.
But won't there be some sort of scale invariance? If you have t to the p for a, you can scale x by something and t by a fractional power of that something, and the metric's invariant.
So you are talking about the adiabatic modes?
I'm just talking about the symmetries of the metric, the invariances of the metric. So there'll be some invariances of the metric when a goes like t to the p. Maybe that can be exploited. I just mentioned.
Yeah.
Okay, I might have
Sorry,
time
the
for one.
question.
Yeah, just like the time translation in inflation, there's also some scaling.
Right, that's exactly right. Yeah, so if it goes like t to the p, you scale x by lambda, and you scale t by lambda to the 1 over p, or maybe I have a factor of 2 somewhere, and that would leave the metric invariant.
Well, there's the dt squared also that you need to worry about.
Oh, yeah, you're right.
I think the best you can do is pick an overall factor.
Yeah, no, you're right, sorry.
But I think the bigger question with that is those kinds of arguments are why it's so hard to get scale invariance in the first place. So often in these inflationary, these alternatives to inflation, you actually have to try to make the field think it lives in de Sitter space for the adiabatic mode. And so all that by construction breaks this kind of symmetry of the background intentionally so you get scale invariance. So I think it's more complicated to extract some sort of general lesson from that.
If I want to make also one further comment is that the vacuum is going to be invariant under probably a very limited subset of this Lipschitz flag symmetry. And I think that's probably just inflation. That's the same that happens for a large scale structure, which is maybe also what Mark had in mind. And there is the matter power spectrum that breaks the symmetry, but otherwise you have the scaling in Einstein de Sitter universes.
In response to Daniel's question, if T is 2/3 the matter contraction, somehow there's a discrete point there which guarantees a scale invariance.
Okay.
Due to inflation. Yeah. Okay. But I didn't explore the symmetry argument.
Yes, actually that is the kind of null-Trader phase. It's very similar to the null-Trader inflation, the ultra-slow models. And there the non-Gaussianity is quite big. It's the other one, kind of ruled out by observations.
Okay, maybe we should move on, and we can, if we have any time, we can come back to these bigger topics. So next we had Soubhik's talk. Were there questions on the expanding the reach of the cosmological collider?
So
again, raise your hand or go ahead.
Soubhik, can I have a question? Yeah. So the new works you're mentioning there, what's the relation between those enhancements in comparison to the chemical potential approach?
Yeah, so they're basically very similar. But I mean, regarding chemical potential, I think like a couple of works before, I mean, a couple of categories of work before focused on like fermion and gauge boson productions, utilizing similar couplings. But here we are focusing on scalars, but still using same sort of inflationary velocity coupling. So del mu phi type of current coupling. So I'd say like the main difference is we are thinking about scalars, and that's why the signal is also at tree level, and that makes like a lot of the calculations much more tractable and controlled. Yeah.
I think previously there's a work showing the scalar field does not have this chemical potential effect. What's the modification?
Yeah, so I think, yeah, so that's also, I mean, we're familiar with that. I think the modification, I mean, there are some differences in approaches. Specifically, I think that there is a particular type of field redefinition you can use that I think some of the previous works thought might make the signal unobservable. But I think we are finding a slightly different conclusion in which we see that like if the U1-like symmetry is unbroken, the phase redefinition indeed have some physical effect, and it's basically it gives rise to like some time-dependent couplings, as I was mentioning, and that can like easily excite particles up to like square root of phi dot. Yeah.
Sorry, I think I misheard that. Could you say that? You said if the U1 symmetry is broken or unbroken. I thought I heard unbroken, but did you mean broken?
Yeah, so I meant broken. If it's unbroken, you can do a field redefinition to get rid of the effect. But we need it to be unbroken. Yeah. sorry, we need it to be broken. Yeah.
So presumably the relation that Jing is talking about is that one, that the previous works wrote a chemical potential for an unbroken U1. Is that a fair assessment, or did I miss some other?
Yeah, so I think I think they also consider some breaking of U1, but then I think there are some difference in the calculations, and I think some of our conclusions disagree a bit. Yeah.
Okay, thanks. Are there other questions? Feel free to raise hands, speak up, write in the chat.
So if you crank up the non-Gaussianity, do you need to worry about getting too much equilateral in conflict with experiments?
Not really. I mean, we are, so you can have like inflaton self-interactions, for example, like del phi to the 4 type of terms, which can give you equilateral or orthogonal, but we don't have this cutoff scale to be super close to Hubble. In fact, they're like 60 Hubble or a bit bigger. And for that, like the typical FNLs you get, they are order 1. So you don't run into complications with the CMB bounds, for example. Okay.
I see, but it's still true that the shape is like close to equilateral. It looks indistinguishable from equilateral around the equilateral configuration, and then as you squeeze, you see the features, right?
That's right, exactly. Okay. Yeah, thanks.
More questions?
So you're saying it's clear that there is no folded singularities anywhere. That's something.
Yeah, I guess so. I mean, we have not actually thought a lot about like the self-interaction mediated non-Gaussian. But I'd say, I mean, for example, if you just write, I think we can write a del phi to the 4 type of operator from this, and I think those kind of signatures has been discussed a lot before. So yeah, I guess you will get the usual orthogonal or equilateral type of stuff, if I understood your question correctly.
The question was that whether related to your cosmological collider signal, there is some other effect whose amplitude is fixed by that could overshadow the signal in the squeeze limit.
I see. Yeah. I think that can be possible. Although I think in that case, just as usual, like to separate out this cosmological collider type of signal, you can hope to rely on the oscillatory features, like as a function of the mass. So, but if you just focus on the magnitude itself, there can be bigger effects depending on how exactly the cutoff scale appears in this self-interaction type of terms.
So I think, Enrico, were you asking about the fact that the particles are physically produced?
Yeah.
I think Enrico's concern is that they're physical particles, and that will introduce these sort of excited state kind of signatures. Have you looked at those?
Oh, no, we have not looked at that. Yeah, sorry, I probably misunderstood initially. We have not looked at that. Yeah.
Thanks.
More questions? Okay, in the interest of time, maybe we'll move on. And then if you have questions, hopefully we can save a little bit of time at the end to circle back. Okay, so the next speaker was Mark Wise. Do we have questions for Mark? Mark, are you there?
Yeah, I'm here. Yeah.
Mark, it's maybe, well, technical / philosophical. Do you think it's possible to compute non-Gaussianity straight up in this conformal Fermi coordinates instead of doing the usual flat slicing and then convert later?
Yeah, I'm not sure. I don't see a reason in principle. Well, the real answer is I don't know. Maybe it would be better to do it like that.
Right.
But the original papers on the subject, they basically worked it out for the endpoints. So if that's all you're interested in, there's just explicit formulas you basically plug into. But if you're interested in more general situations where all the endpoints come in certain limits, it would matter, then there could be a lot of value in trying to approach it the way you say.
Mm-hmm.
But I don't, I haven't thought about that. I don't know.
I see.
Really how possible it is.
Thanks.
I also had a question, if I may. It was about, yeah, it was also maybe related a bit to what we was asking, that so usually when we introduce this conformal Fermi coordinates, we remind that they are valid in the squeeze limit. The patch that they cover is of order k long to the -1.
Right.
So, but the assumption, if I remember correctly, the assumption that one needs there for this to work is that, like, the time derivatives of the metric are behaving in some way. And I was wondering if in that case that you were discussing in your talk, the second part, where there is some in some sense time dependence that survives at late times, this is invalidated in some way. So the usual statement that you make on the size of the validity region of this conformal coordinate system is changed from the original papers.
Yeah, I don't think so. Even though we have some mode evolution outside the horizon, you get this eta to the alpha minus. Alpha minus is still pretty small. So the time derivatives, it's a modest time dependence. So I don't think it invalidates the conditions. Yeah, I think it's still okay. In fact, the original papers, the part that we use, they also give the part of the formula involving those time derivatives, which we used. We didn't, usually they're much less important because the modes are, they're constant outside the horizon.
Yeah,
those are,
the time derivatives are going to zero very quickly.
Right, and then you use the contribution from the breaking of scale invariance. And that's what canceled the Maldacena calculation. But in our case, we imagined, well, they are. I mean, there's, the violations of scale invariance are small, the tilt is small, for example. And so to get an effect that was large enough, we had to do a situation where there was some time dependence.
Mm-hmm.
But sorry, Giovanni and Mark. So it seems to me that the coordinates are well defined irrespectively of the time dependence. I mean, I should know very well, but my understanding is that you can always create a little noodle in time for which the coordinates are valid at all times. This is just for the coordinates themselves. Then we're going to apply that to the calculators, and that's where we're neglecting some time derivative. But just from a GR perspective, I think you can always choose those coordinates.
Yes, but I thought that one of the perks was also that the difference between the conformal and the normal Fermi coordinates was that the conformal, you can define them, but the useful fact is that you can follow the patch from horizon exit to re-entry, and this was in your original paper. It was a nice plot by
exactly.
And this is related to this. I thought that to require that the time derivatives were behaving in some way, because now the conformal coordinates have like the Riemann of the conformal metric, and this contains both spatial derivatives with scale as k long squared, but also time derivatives, and then you have to check what the time derivatives do, because the Riemann is multiplied by the size x of your conformal.
But that's the Riemann with spatial indices. But okay, we can discuss it privately.
Yeah, fine. That was my kind of worry about it.
They're valid anyways, but I'm happy to talk to you.
Yeah, I think the coordinates are valid.
Okay.
Because it's RIJKL, as was said. But I think if the time derivatives are too large, it still might be a problem that there might be higher order effects that are.
Well, sorry. Yeah, because it shouldn't be only R. It should be R mu I nu R mu I nu J delta xi, delta xj, you know, the components of the metric. So there are also the zero, R0I, 0j. That was my worry, but okay, maybe we can discuss later.
Oh, yes. Okay.
Yeah, sorry, I didn't want to hijack the conversation.
More questions?
Hi, Mark. I have a question about calculation about all those 5, 6-point correlation functions.
Mm-hmm.
Did you? It looks like complicated equation calculations, but the result is not that complicated. Do you go to some special limit when doing when calculating those diagrams?
Right. So we did work in the limit of smallish m, and I guess it's more, we called it mu, but it's more commonly called rho compared to the Hubble constant. So that simplifies what parts contribute a lot. And then I don't remember, but it might have been for something like the 6-point, we only calculated it in the relevant limits. I don't remember whether the lower ones we calculated in general and then took those limits. I mean, K and the various wave vectors. But we always worked in small mu and h. And it might be some of the methods that have been recently developed make those calculations a lot easier. Like, you know, effective field theory developed for low modes. But we just did it straightforwardly in informalism. I just wanted to say one thing. I didn't really stress it in the talk, and that so in the end for the bispectrum, we for galaxies we had this basically. If you look at all the wave vectors small compared to the size that collapses to a galaxy, you get something that goes like 1/q⁶ in quasi-single field inflation. That'll hold in a lot of models because it, you know, it basically depends on the infrared behavior of Feynman diagrams. And that's set partly by their structure and, you know, conformal dimensions of operators. So I think that's a very generic behavior. Not always, but in a lot of models.
I see, thank you. So usually in the effect of non-Gauss entities on galactic halos, the effect, I don't know if it's a general conclusion, but at least people study the local limit and have argument saying that's the limit where it affects most. Since you have studied the limits deviating from that local limit, do you see any, do you verify that picture that the effects going down as mass increases? Of course, not as much as Boltzmann suppression, but towards h, or you see some interesting distinctive features from the local limits.
Well, you see it like instead of, so the enhancement, let's say from the compressed limit in the of the 4-point function from the 2-point function for the 2-point function of galaxies. So in the local limit, it just goes like 1/q³. And if you have a massive particle exchanged with the mass less than the Hubble, it's not 3 in the denominator, but it's 3 minus something that goes like m²/h². I don't remember the exact coefficient. And so you can see that it's less enhanced in the infrared when you have a massive particle exchange. But if m/h, you know, if m is like 1/3 h, then that's a, you know, then it's 3 minus a tiny number. It's almost 1/q³. And I don't think you'd ever get the really local limit unless it was a massless particle exchange. And, so it doesn't even need tree exchange. It could be a loop Feynman diagram. You look at the infrared and you get that same 1/q³.
I see. The change is mostly from a k dependence. So the amplitude, the amplitude of the signal is not affected much, right? As you vary from.
So the amplitude is more model dependent, I believe, than the literal scaling with wave vectors when they get small. And so in quasi-single field inflation, where you use the potential part, you could make it. So we only looked at like a a field cubed part of the potential. But you could make it as big as you want. The restriction comes from the CMB limits on FNL.
Right, I understand that. So I guess I was asking more about fixing those coefficients, but compare the difference between low mass and higher mass. So those dependencies.
Okay, right. So yeah, so you got some enhancements by looking at low mass.
Okay.
But those enhancements were also just in the in the general 3-point function, and so they just got constrained. The whole thing, V triple prime, the whole bundle just gets constrained. I don't think it helps you with this, with enhancing the effects in biased, for biased objects.
Okay.
There's so just some overall, pardon?
So the effect when the mass goes to 0 does not cause some runaway, the blow up behaviors, because
well, I think you might get a blow up if you have m squared plus mu squared as they go to 0. But we just, we just took those. We didn't go to incredibly small, and we just took the constraint from FNL. So V triple prime divided by m squared plus mu squared has to be less than something.
Okay.
Otherwise, you screw up the CMB.
Okay, I think we need to move on to Sebastien, so we can try to get back on schedule. So,
could I just say one tiny thing? I might have to leave early from the meeting, so I just want to thank everybody, particularly organizers, for a great meeting.
Let's echo that. So, okay, thanks, Mark. Okay, last in this session we have Sebastien Reneaux-Petel. Do we have questions for him on multi-field stochastic inflation?
Maybe I can ask one. Hey, Sebastien.
Hey.
Since here you are studying this stochastic approach, then do you expect some non-trivial result for the light fields?
Do you
maybe
expect
it's ultralight one?
Do you expect what? Sorry.
Some non-trivial results for the light fields. Very light one.
Not sure to understand. Well, the stochastic framework is precisely meant for the light fields. I mean, especially, the effects are especially important for the quantum diffusion for the light field. So yes.
And there will be some constraints on the mass or some.
Not sure what exactly you mean. Usually the standard approach is applicable. Background plus perturbation theory and stochastic inflation is precisely there as one of the methods to deal with late time infrared divergences of the light scalar fields. So typically, if your field is m over the h, you have the fluctuations are more suppressed, as you know, on super Hubble scales, and very suppressed when m is greater than 3/2 of h. So in that case, you have basically no stochastic effect.
I just wonder if I need to worry about this approach for the ultralight case if the mass goes to 0.
Oh yes. Well, when the light is the things on which you worked, I would say orbital inflation stuff, with exact masses being 0. Well, then by definition, the quantum diffusion expect to play a role,
right?
Because there's no classical motion. So yes, that's this setup can be one of the things to which our formalism can be applied to, especially because it's in generic curved field space.
And what would be the consequence you would expect there?
That would be interesting to look at. But to be honest, I haven't looked. Took us a lot of time to derive the general formalism, but what would be the practical consequences in this type of scenario? For the moment, I don't know.
I see. Yeah.
More questions?
So now you know how to handle covariance in field space. Do you think you can apply these lessons to study the effects of infrared gravitons and be careful about GIF invariance and stuff like that.
Sorry, let me try to reformulate your question. Now you want to ask the question with the gravitons.
Yeah. Imagine you run into similar types of subtleties because of diffeomorphisms and stuff like that.
Yes. That's a good question. I didn't ask myself the question before, so short answer is I don't know. But given that we paid particular attention, which was actually not studied at all in the literature, to pay attention to covariance and the link with the discretizations. As you know, usually physicists just write Langevin equation. They don't care about the discretizations, Ito, Stantonovich. And actually they should, because the chain rule is only verified in Stantonovich and so on. So, I mean, we dealt with this issue, imported the knowledge from statistical physics and so on, and found what we think are good ways out. So that may help for this case to deal with covariance in general. But I haven't studied this precise question, but that's interesting.
I think the field space of the metric itself is highly restricted by the different variants of the metric. So I think in the sense that you meant it, with no derivatives in space-time, it's the field space on the manifold of vacua of the field. Right. I think for the metric that's not going to be particularly interesting. I think in this formalism.
Okay. I have to think more about the question, which I haven't thought about, but.
Okay, sorry for abusing my powers. More questions.
Can I ask something?
Go for it.
So, hi, Sebastian. So I get a bit confused. Probably you clarified that in the talk, but I didn't understand. Do you get the covariant field equations at the end of the day in both formalism, like both Ito and Stratonovich, or in one of them?
I would say that the question is ill-defined because a given set, a given physics can be described with different discretizations, and they would be equivalent. But then, for that, you have to change the form of the differential equation. Or the reverse is you take a differential equation, stochastic differential equation, sorry. If you interpret it differently with different schemes, it gives different physics. So if you take that into account, the usual equations that people write, the one that you can derive naively, they would make no sense. They would not respect covariance in Ito. However, they would be okay in Stratonovich under some explanations that we explain in the paper. And we can equivalently derive Ito Langevin equations, which are different, but which do respect covariance in a more manifest manner, and that can be easier used for numerical computation, say.
I see, okay.
We only have time for one more, and then we should move on to the next session. Any more questions? Okay, going once, going twice. Okay, well, so I think in the interest of getting closer to on schedule, we should thank all the speakers in this session, including Xingyang and all the talks. So thank you all. And I'll let Guy decide when the next talk is going to start.
Maybe we give a 5 minutes break.